Hi everyone, so today we're going to talk about fossils and you are going to complete a note on Earth's early history. So first of all, what is a fossil? Well, a fossil is the preserved remains of an organism from the past, but we can also think of a fossil as just the trace or remains or imprint of an organism that existed in the past. In order to be a fossil, the remains have to be older than 10,000 years. Fossils can only exist in sedimentary rock. If you think about fossils existing in igneous rock, well, that's not possible because igneous rock is just cooled magma. And it also couldn't exist in metamorphic rock because the temperature and the forces would completely destroy the organism. There can be some remnant of the organism itself, like an imprint, maybe a fossilized piece of excrement, or even just a chemical signature that is called a trace fossil, and that can also be considered a fossil. So can radiometric dating be used on a fossil? Something like dating uranium isotopes or using carbon-14 dating? The answer is no, probably not. Carbon-14 dating can only be used on organic material that's less than 50,000 years old. And remember, you have to have organic material around still in order to use carbon-14 dating at all. Carbon-14, by the way, has a half-life of 5,730 years. So if you are dating a fossil that is many times older than that, there's not going to be enough carbon-14 around, even if you are able to preserve any organic matter from that organism. Now, radiometric dating often is successful when you use another type of isotope, like let's say uranium isotope. However, you don't find uranium in organisms. So any isotope of uranium that you find in a fossil would really just be dating the rock around it and not the organism itself. So there are a couple of different ways that fossils can be preserved. The first and best method of preservation is called original preservation, and that's when you actually are able to preserve soft tissue from the original organism. It's very rare and you need very special conditions. Here are some examples. Organisms can be preserved in tree sap or amber. You can have some organisms that are frozen in glaciers over very, very long periods of time. And some organisms are able to be preserved in some types of sedimentary rock, but only if the organism was buried really quickly to prevent any decomposition. You also need a very oxygen-poor environment to prevent decomposition. Here's a really creepy example. This is an oil shale deposit from Germany. Please feel free to click the links on the SmartNote to see more kind of creepy photos. So as you can see, these organisms were buried very, very quickly. And so if you look closely, even the fine detail of hairs on their tail were preserved. So this is an example where carbon-14 dating could actually be used. And finally, here's an image that you've probably seen before, some sort of an insect that's been solidified in amber. Now that insect is really well preserved, and of course, the actual carbon that existed in that original insect would still be there. Another type of preservation is called mineral replacement. So if you have an organism that has a lot of hard parts in it, and over time water with dissolved minerals in it percolates through all of the hard parts, like a shell of that organism, the parts of the original shell will dissolve and be replaced by that new mineral that was present in the water that's percolating through. Here's a really pretty example of a shell where the compound, the mineral in the shell itself, was actually replaced with opal. So you get a really beautiful specimen. This is an example of mineral replacement. This is technically called coprolite, but as you can see from this link, what that means is it's actually fossilized poop. So this is technically a trace fossil, evidence that an organism was around, even though this isn't the organism itself. Here's another example of mineral replacement. So these interesting shells were replaced with a different mineral. This one was chalcedony. So chalcedony wasn't present, those atoms, that chemical wasn't present in the original organism, but now it is because of mineral replacement. Here are two other interesting ways that fossils can be preserved. Recrystallization is when a mineral that's already present in the shell or hard part of an organism doesn't get replaced, it just rearranges itself into a slightly different form. So it's a different name of mineral, but it's the same chemical compound and same chemical composition. So for example, If your shell is made up of calcium carbonate, in the end, after recrystallization, it's still calcium carbonate, but the crystal form and the name of the mineral has changed to something different. Another type of preservation is called permineralization. That's when a mineral fills in the cavities that are left by an organism. So imagine you have an organism that has all these empty cells in it. Well, a mineral can come in and fill up all those empty spaces, and that's called permineralization, and it really helps to preserve the organism and what it originally looked like. When both permineralization and mineral replacement happen for an entire piece of wood, it creates something called petrified wood, which you may have heard before. It's a perfect, durable specimen, and it helps to preserve the wood down to very, very fine detail. Here's an example of a piece of petrified wood that's actually 230 million years old, and you can actually see the fine detail. Sometimes you can even see tree rings in these specimens. So what happened was minerals replaced the cell walls of this wood, and then a different mineral came in and replaced all the cavities that represented the inside of those original cells, creating a really nice specimen that we can still see in lots of detail today. And here's actually an example that I have of a piece of petrified wood. The next example for preserving fossils is a mold or a cast. So a mold is formed when the body of an organism makes an imprint on some other surface, usually something like shale or mud. Eventually, the organism's remains decompose and get washed away, but the imprint is left. You've definitely seen these just out and about. If the mold is filled in with something else, like another type of rock or another type of mineral, it creates a cast. So a three-dimensional representation of what that organism may have looked like. Finally, we have trace fossils. So a trace fossil is just some sort of record that an organism existed in that area without an actual fossil or any part of the organism being present. So if you can spot animal or organism footprints, if you can spot the track made by an organism that could actually move from one point to another, if you can spot any coprolite, which means poop. And here's another very common one. If you can find a stromatolite, here are examples of stromatolites that existed sometimes billions of years ago. And here's why they're important. Because many cyanobacteria that existed, again, billions of years ago, built sediments around themselves to create a sedimentary rock called a stromatolite. And they have many layers in these rocks. Cyanobacteria were one of the earliest organisms on Earth and responsible for our oxygen environment. And so stromatolite fossils from these ancient cyanobacteria can be found today, and they can be some of the earliest evidence that these organisms existed. Here's an example of a sand stromatolite from the Lower Cretaceous period, which was 120 million years ago. Here are some other interesting fossils that I want to show you. This is an example of a leaf fossil. This leaf fossil is from 50 million years ago. This is an example of an ammonite, which is something that you can commonly find in shops. It's a shelled organism. This one is actually from the Lower Jurassic period, 170 million years ago. This one, as you can see, is a mold. Here's another example of an ammonite. This one is from 112 up to 99 million years ago. So it's from a more recent period. And you can see that the empty spots in this ammonite shell have actually been filled in. So this is a good example of likely mineral replacement as well as permineralization. Here's an example of a trilobite. This trilobite is likely from the Devonian period, so between 359 to 416 million years ago. And this one is likely a cast. This is an example of an interesting specimen found on Lake Erie. This is actually a horn coral, so it's a fossil of an ancient coral. And here's another example of a stromatolite. This stromatolite is actually a specimen recovered from Ontario. Now let's talk about the timeline of fossils. We've talked about index fossils before, and index fossils are essential if we want to date or put a rough time frame on layers of sedimentary rock. In order to be an index fossil, that fossil has to have existed in many different geographic locations around the world. So it had to be widespread. It also has to be very distinct, so easy to identify from other fossils. And it has to be short-lived. So it was only on Earth for a very short amount of time. That means that if you find it, you have a very clear window as to when it existed. Here are some examples. I will not be pronouncing these as much as possible. However, what you can see are some distinct organisms that only existed for short periods of time. And here I've put a little bit of a timeline on when these different organisms were around. Trilobites are very common as index fossils because they're easy to tell apart. And by the way, this region right here, this is about the time when the rocks in the Niagara Escarpment formed. So using one of your previous notes, actually the first lesson from this unit, I want you to label this diagram in your note with some major events. So for example, when was the first vertebrate land animal around? Hint, it was about 380 million years ago. Label when the first mammals were around, when non-avian dinosaurs were around, and when the first animals were around. Here are some slightly better pictures. Here are some trilobites, and you can see different trilobites have different features, which makes them easy to identify. This is a shelled organism, another shelled organism, I will not pronounce it. And finally, a leafy, a very simple leaf organism. Now for an example, another puzzle-like example. Here we have 4 different rock strata that were all formed in different regions at similar times. In this rock strata, we've captured some trilobites. Now on the next page, I'm going to show you a diagram from your textbook that will actually tell you over what years these trilobites were actually around. So we will be able to put a rough estimate on the time frame of all of these layers. There's also a key bed, a volcanic ash layer. Now let's say we radiometrically date the material in this ash layer, and we know that it's pretty much spot on 400 million years old. What we need to do is we need to correlate these layers, keeping in mind some are missing because some have been eroded in different layers. So let's go ahead and take a look at what we've got. So I've got my line tool, and I'm going to start by outlining the different layers, the different adjacent layers that I know are similar. This will help me make sense of the puzzle to begin with. The other key piece of information here is anytime you see a trilobite, assume it belongs in the layer that it's in. Okay, so now let's start making sense of these layers of strata. If we take a look at the trilobite at the very bottom of the screen here, we can see that it exists in this strata, as well as this strata. It's also the bottommost trilobite in this strata, meaning it's got to be the oldest trilobite. There's also limestone directly underneath it and shale directly underneath that, which means these are our 3 oldest layers: shale, limestone, trilobite number 1. So on your page, you're going to draw this as the first 3 layers. Now we look a little bit further. There's our first trilobite. Above it is sandstone. That's clearly been eroded in these 2 strata. Above that is limestone. And then above that, we have trilobite number 2, which also shows up in this strata over here. So we've got trilobite 1, sandstone, limestone, trilobite number 2. Let's fill that in our timeline as well. So now we're here, this layer, trilobite number 2. Here it is again down below on strata number 3. And we can see right above trilobite number 2, we've got limestone, dolostone, and then our key bed, our ash layer, which also exists in this strata over here. That matches up. So now we're at the 400 million year mark. Above the volcanic ash layer, we've got sandstone, we've got shale, and then we've got our last trilobite, this guy up here. So now we can fill in these layers on our diagram. This is kind of a nice streak of layers, uninterrupted. Now finally, the last piece of the puzzle, I've got trilobite number 3 at the top here. And I can see above trilobite number 3, I've got limestone and dolostone as my upper layers. But one thing to keep in mind, go back to strata number 1. There's my key bed. Here's sandstone and shale. However, there's an eroded layer. And the thing that's missing from this eroded layer is actually trilobite number 1. And so here I can see that above trilobite number 1, there's actually limestone, dolostone, and then some more limestone again. So completing my strata here, I end with limestone, dolostone, limestone. Now that I know that, I've got all of my layers sketched out, I'm going to try to put a timeline on these different trilobites. And in order to do that, in order to use them as index fossils, I need to know what time frame they existed on Earth. Now on page 509 of your textbook, there's a really handy table that I've sort of tried to recreate here. And here are some index fossils that are all trilobites. Now if we look closely, we can see that this is one of the ones from our diagram. This is trilobite number 1 actually. This one, which looks like a pickaxe, is trilobite number 2. And this one here is trilobite number 3. So we can see exactly what range of time each of these trilobites was around. So we can put a rough estimate on our trilobites now. So let's take a look at what we've got. Trilobite number 3 existed anywhere between 359 to 299 million years ago. The key bed, our ash layer, was 400 million years ago. Trilobite number 2 was anywhere between 444 to 416 million years ago. And trilobite number 1 was anywhere between 488 to 444 million years ago. Knowing that, we've got a little bit of a rough timeline going for all of our layers. Here it is. We know that between trilobite number 1 and trilobite number 2, these layers of rock could have been laid down anywhere between 488 at the earliest, all the way to 416 at the latest million years ago. Now between this layer of rock and our key bed layer, where we know the date pretty exactly, these could have been laid down anywhere between 444 million years ago all the way to 400 million years ago. Next up, the key bed was again 400 million years ago, but all the way up to here, these layers could have been laid down anywhere up to 299 million years ago. So just by finding these index fossils, we're able to put a rough timeline on our layers. Now what you're going to do is click on these links. These are PBS videos. You're going to watch these links and make your own note, summarizing some cool information about Earth's early history.